Good morning, mathematicians. We are live from the new place. I'm trying to be pretty quiet because I wake up a lot earlier than my roommate. But I think the microphone makes that fine. I don't know. Should I turn up the volume? I don't even have chat open yet, so I don't know. What to yap about today? Good morning, Edit Smith. Yeah, new background reveal. I don't know if this will be the usual background. Yeah, we'll see. We'll see. Okay, what were we talking about yesterday? We were yapping about a bunch of crazy stuff. Oh yeah, thinking diagrams. Well, I mean, New Wave Infantry didn't show up, but I guess we did, I did finish giving an overview. Two? What do you mean by that? Oh, yo. Oh, I see. Hi. Yeah, what to yap about today? Oh, there's this paper of David Rowe that I'd like to read more. I don't know if I shared it with you guys yet. Rowe periodic. Yeah, maybe just search this. The inverse Galois problem for periodic fields. This is the paper. Yeah, so basically, for those of you who might not know, the inverse Galois problem is, fix a field. So of course, if you have an extension of fields, which is Galois, you can look at the Galois group of that extension and then transport information back and forth between the fields and the Galois groups. But the inverse Galois problem, this asks, so basically the inverse Galois problem for the field F says this: for any finite group G, does there exist an extension E over F such that the Galois group is isomorphic to G? So if you fix some field, is it possible to realize every finite group as the Galois group of some extension of that field? And so the inverse Galois problem over Q, for example, is wide open. The inverse Galois problem for a finite field is extremely false. I don't know what it means to be extremely. It's very, very false. Very, very provably false. Wide open, but I think it's proved for solvable groups. for instance. So we do know it in some cases, and other cases. You actually wanted to make a video on it. Oh, nice. Nice. Those are all great things to make videos on. What is it true over? Isn't it true over like C adjoin Z or something? There's definitely fields where it's true over. Function fields over algebraically closed fields. I see. Well, can we trust AI? It's saying that, function fields over p-adic fields. I see. If I had to work as a mathematician with the result of it healing cancer, but the North Korean would be taking the credit? Well, I'm not sure I understand the question, because the way it is phrased, you're saying that if I had to, but then that means I have to. So, or do you mean that the only way I could be a mathematician is if I worked as a mathematician healing cancer, but then the North Koreans would take credit for it? Yeah, if you could clarify, I can give you a better answer to your question. Because if that's the case, I don't know. That might not even be a good use of. I mean, maybe if there was some sort of actual math that one could do, where the result was healing cancer, but if I was just spinning my wheels trying to come up with something, then no. Then no. Good morning, quality content. But that brings us to the Galois problem over. Okay, so Galois problem. So inverse Galois problem over Q, wide open, major open question. Inverse Galois problem over finite fields, definitely false. Inverse Galois problem over everyone is sleeping, Paul Maurice. Yeah. I don't know if maybe I can talk louder, but this is my first day in the new place, so I don't know what's a good volume level. Finite over finite fields, definitely false. And we know all of the extensions of finite fields. That's very easy to work out. It's true over this function field. And so, of course, a question I'd be interested in, what about over the p-adics? It's false. But I don't think we have like a complete understanding of which groups are realizable and which ones aren't. Or maybe we do by this paper. So, this is really interesting. So we describe a method for computing the number of extensions of QP with a given group G, founded upon the description of the absolute Galois group. Because this description is only known for odd P, fascinating. We apply the results of counting such extensions of G of order up to 2000, except for those divisible by 512, weirdly. For those primes. And they highlight a list of non-examples. Motivated by this list, we proved two theorems about inverse Galois problem for QP, one giving a necessary condition and the other giving a sufficient condition. Very cool. Yep. Such a weird abstract, is it? What do you think is weird about it? Nothing struck me as particularly out of the ordinary. Yeah. That's true, Rod. And, yeah. A lot of problems in number theory, arithmetic geometry seem to be solved by proving theorems giving bounds on what you have to search, and then exhaustively searching every. Yeah. Perhaps. I guess we'll take your word for it. I have no sense of if that's a lot or, yeah. This thing about vanishing of algebraic K-theory of QP that was discovered by computation and then proved rigorously. Really? What does that result? Vanishing K-theory of QP? Oh, ZPN. Exact bounds for even vanishing. Or how about on the K-theory of this? What happens for Q2? I don't know, Paul Maurice. Everything goes wrong when P equals 2. I mean, this is just the way life goes. But yeah, I wonder, when's this paper from? 2018. I wonder if anyone's worked on a P equals 2 sequel. But yeah, there's this researcher in my field, and she definitely does things when P equals 2 and has an understanding with certain things like supracuspidal representations of p-adics and how the theory differs. And so she often asks during at a talk, what about P equals 2? Yeah. And much like Pluto, we will eventually abandon 2 as a prime. We should already, and I have in my heart. Anywho, I give an explicit algebraic description based on prismatic cohomology of the algebraic K-groups of these rings. The algebraic description allows us to describe a practical algorithm to compute individual K-groups, as well as to obtain several theoretical results. The vanishing of even K-groups in high degrees, the determination of orders of odd K-groups in high degrees, and the degree of nilpotence of V1. Symptomic, that's a word that came up again recently. I've never learned the... Can you request a topic for next time? You can request a topic for now, Jay. I mean, you can always... This is the point of office hours. Just ask away. Ask anything at any point in time. I mean, we just had a question about what I would do if I had to work on cancer healing math that the North Koreans would steal credit for. So just you don't have to ask. Just ask away. Well, we can talk about anything. Um. Oh, well then, please do keep writing your notes on symptomic cohomology. I don't know anything about it. It just came up. I was reading. What was I reading? This document here on Stacks, I think, and they mentioned. They said the usual FPPF, FPQC, but then they said something about symptomic. So, can we compute some Galois cohomology? Probably not. Let's see. Off the top of my dome, no. If you gave me like a day, we could probably. That's one I could like probably promise you for tomorrow. Notes on Galois cohomology. You would like me to go through free groups, adjoint functors, lifting, and the universal property in detail. Yes, you've read Wikipedia. Okay. Well, I see. Well, that I can do. That I think is easier for me to talk about off the top of my dome. So let's do that. Let's talk about free groups. So a free group is basically a process that allows you to turn any set into a group where so if we have a set, I don't know, X, then the free group fx will have a number of generators equal to the cardinality. How can we do this? Well, let me maybe start with free abelian groups, just because the description, the way to like formally describe it is a lot easier. So let's start with free abelian groups. So what do we do? So we're going to take a set X, and we're going to imagine that we're basically going to, so suppose X had 3 elements, A, B, and C. And we're going to form a group where the elements of X are the generators of that group, right? So I want to be able to make sense of something like A plus B plus A plus A plus C, for example. So I want to formally make sense of this. And of course, since this group is abelian, I can write these in any order, right? So my A's, I can always shuffle over here, and I can write this as 3 dot A to mean the sum of 3 A's plus B plus C, right? So so in other words, every element of this group is just going to be the choice of some integer. We'll also want negatives to have inverses assigned in front of each 3 of these elements. So in other words, we could view the free abelian group as the set of all functions from X into the natural numbers There's one other important thing, though. We need to say that it has finite support. So, yeah, finite support. Or maybe... So what do I mean by that? The support is the set of all of those x in x such that f at x is not equal to 0. So this is vacuously true in our case of x having just 3 elements, but if x were infinite, I don't know the real numbers or whatever, some infinite set, then the thing is we just don't want to have to worry about, summing infinitely many things together, because then in order to make sense of that, we would have to put some sort of topology on there. Okay, so that is a free abelian group. Hey, Julie. So free abelian groups, and what is the group operation on here? It is just going to be so two functions. Well, what do I have to do to tell you what the sum of two functions is? Just tell you its value at every one of these. Someone should find out if they have some sort of motive, and then make it really explainable. You can get away with never using cohomology again by just using derived push forwards. Yeah. Professors hate this one simple undergrad life hack. I guess it's not even an undergrad life hack. Reviewers hate this one simple research hack. Replace all cohomology with derived push forwards. Yeah, so just as an example to see that this works, imagine you wanted the element 2a plus b, and you had another element c. I don't know, maybe b plus c is the other one. Good morning, Ken. So what's the function associated to this? Well, it'd be f at a is 2, f at b is 1, f at c is 0. What's the function associated to this? It would be g at a is 0, g at b is 1, g at c is 1. And so then what would be the function f plus g at a would just be the sum of its values at a, which is 2. F of g at b would be 1 plus 1, which is 2. And f plus g at c would be 0 plus 1, which is 1. And so going back to the element description, it should be 2a plus 2b plus c, which exactly aligns with what you would intuitively expect about adding these together. Okay, so that is free. So free from sets into abelian groups. I'm guessing, Jay, that you know about functors, since you asked about adjoint functors. So this is, in fact, a functor. So I've just told you how to take sets and produce abelian groups. So I've told you what it does on the level of objects. What does it do on the level of morphisms? Well, I claim that so if it's a functor, I need to produce a morphism between my free groups. Maybe I should use phi because I was using things like f for functions. So phi between sets. So, well, let's think about it. If I had, right, f of x is the set of all functions from x into z. Oh, have I done things wrong? Functions x into z, and I want to get from that two functions into y. Is it a covariant functor? Because it seems it should go the other way. Or sorry, contravariant. Yeah, maybe this is a contravariant functor. Have I made a mistake? I don't think free should be contravariant. Oh, just apply phi on each generator, right? I was just thinking in terms of pullback. Yeah, that's true. Right. Okay. Yeah. Thanks, Harad. Good morning, Lola. Right. So if we have a function, right, f of x to z, we can build a new function out of y where, right, I'm trying to think of the way to formalize this with functions. So like of course, if we had 3a plus b plus 2c, we could just quote unquote apply this to get the function 3 phi a plus phi b plus 2 phi c. So I guess f of phi of f would be the function. Yeah, here's how we define it. So it'd be the function on y, which is defined to be, it's defined to be f at x if there exists sum through the preimage. Yeah. Right. Right. So it's the sum over x in the preimage of y of f of x. That's interesting. That's very much like integration over a fiber. I wonder if there's more to this analogy than that. I mean, because it is a kind of push forward, right? It is a kind of push forward between function spaces, right? Yeah, everything is fiber integration. Yeah, well, push forward is fiber integration, and earlier, as you mentioned, all cohomologies can be replaced by derived push forwards, and so therefore all cohomology is just derived integration over fibers. Yeah, okay, so the point is we have a functor from sets to n abelian groups. And the claim is that, well, in general, if ever you have a free functor, you should always expect that it has an adjoint given by a forgetful functor. By the way, yeah, Ken, on that question, not only does topology have free objects, but the forgetful functor from topological spaces to sets actually has two adjoints. I forget which goes on the left and which goes on the right, but one of them is the discrete and one of them is the indiscrete topology. F lower shriek, yeah. Yeah, F lower shriek is... Well, F lower shriek is the right, because F upper star is on the left of F lower star, and then I think it switches for the shrieks, right? So F lower shriek is the left, isn't it? I have to look this up every time I use this. I think about such things on the daily. You'd think I would remember, but no. Oh, I always forget top chat. I gotta change it to live chat. You guys gotta yell at me more about this stuff. Left adjoints in general tend to behave like fiber integration. Okay. That's actually a very good question, Jay, about what happens when you compose free and forgetful functors. Well, in general, I don't know if there's anything so interesting to say, but let's look at so what does it mean to be adjoint? What does it mean to be adjoint? Well, I always forget. Is free on the left? Is free on the left or is free on the right? I always forget. Wait, we can go based off of Ken's comment. Indiscrete is right adjoint. Discrete is left. Okay, so free is on the left. Free is on the left, I think. So it should be like free X, and here's an abelian group, right? We should have natural isomorphisms. Free is left. Nice. Yeah. And well, so an interesting thing to say is something about the one of the many. So this is sort of, possibly one of the first definitions that you'll righty tighty lefty loosey. I remember, but lefty loosey, lefty loosey makes me almost think about forgetful. But then again, loose, free, yeah, I don't know. But I do think about that like literally every time having just moved, I was screwing and unscrewing a bunch of stuff, and of course in my brain, that sticks. But remember, an alternative definition of an adjoint pair of functors is to say that there is a pair of homomorphisms. So let me think. The unit of a junction is, I think the unit of a junction is this, and the co-unit is this. I'll double check myself in a second. But the point is that there's an alternative description of what it means to have a natural isomorphism between these Hom sets, which is the unit should be the other way around. Damn it. So set. It's like sending each generator to the corresponding element in the underlying set. Yeah. And then the point is that these, so saying that there's a natural isomorphism here is equivalent to defining a pair of natural transformations from the identity functor to the composition of these two functors. And in fact, so this is like a general, this isn't even just about like free and forgetful. This is like a general statement about, this is a general statement about adjoint functors, is that you have a pair of natural transformations satisfying a certain universal property. You can send me a screenshot, Matthias. I am probably logging off soon. You can send me a screenshot, but yeah. Yeah. Maybe I'll answer. Is it a general exercise to prove the equivalence? It is a general exercise, and it's a very good exercise. So, I mean, you definitely want the universal property. So, unit of adjunction. So let me just get it right. I could sit here and work it out if I had to, but anyways, I mean, I would go to Wikipedia, look up the unit of adjunction, and yeah, basically between these two things, I mean, you need to build a sequence of maps, right? Or call it phi xa. Right? You need to define a series of bijections between these sets. And so the challenge is then use the definitions, use the universal properties of these two things in order to define a bijection and vice versa. In some sense, monads allow you to access the theory of groups without leaving the category of sets. And that's why monads are useful for Haskell. They let you access the outside world without leaving the pure category of Haskell types. Interesting. That is interesting. Well, I think on that interesting note, I am going to end the stream for today. But Jay, maybe we'll come back to we can come back to this tomorrow. What else did you want to know? Free groups, adjoint functors. Yeah, maybe we can go through maybe proof of adjointness in more detail. Though I'd say these are good things to go and try and prove. Lifting and the universal property in detail. Yeah. Well, which universal property? Anyone? We can definitely talk about these things tomorrow. Another thing, the commuting triangle lives in which category? So you mean for the universal property? Well, this would be, so you just have to track through each of these, right? So in this setup, F is a left adjoint functor, and it goes from a category from D to C, right? So in this case, we can see that F of Y, so that must be the functor F applied to an object Y of D, so that means F of Y must be living in the category C, right? And so this whole triangle must be happening in the category C, right? So you can see, for example, for each object X in C, indeed, X is in C. And then finally, well, X is in C, so G, which goes from C to D, right? You apply G, that's in D. You apply F, you're back in C. So indeed, all of these objects are in C, and you can, but I mean, yeah, your hint is as soon as you realize one of them is in C, of course, all of the others have to be for it to make sense. But there's two, right? There's two triangles. There's one for the co-unit of a junction here, which is happening in C, and then there's another similar triangle, which is the unit of a junction, and this is happening in D. Okay, signing off for real now.